We are now over with the first part of the energy balance. That is, we examined the heat conducted into and out of the differential element Qx and Qx plus dx, which in the energy balance represent the energy into and out of the differential volume. The heat conducted can be expressed in the form of a Fourier's law. However, the situation can be more complex if we, beside the conduction, also have heat generated or consumed within the system. Several phenomena may cause heat generation or consumption within a system or the volume we are observing. Reaction heat during exothermic or endothermic reaction might cause heat generation or consumption. Then heating or cooling due to various physical or chemical processes such as convection or radiation or the evaporation. There are some more, of course. There could also be work done either by the system or to the system. To express the heat generated within the volume, we multiply the heat generation rate times the differential volume. This is because the heat generation term is a volumetric phenomena and has units watts per unit volume. To get the absolute generated heat, we need to multiply it with the volume we are observing. In our case, this is the differential volume, which is simply the area times thickness dx. After considering all three components of the energy balance, we are now left with a term that expresses the changes in the amount of the stored thermal energy. Note that this change of the thermal energy is only due to the changes of sensible energy, which is the energy related to changes in temperature. The latent energy, due to the change of phase, is not considered. We write the change in the stored energy as the product of the differential mass of the differential volume times heat capacity times the change of the temperature over time. Differential mass can be expressed as the differential volume times the density. And differential volume is again area times dx. So we see that the changes in the amount of the stored energy it can also be zero for the steady state system, but it is a result from the conductive heat energy transfer and the heat generated within the system.